So this section deals with the central limit theorem. And the central limit theorem deals with basically the averages of samples. So what we were looking at before, like with normal distribution, a bell-shaped curve, all the data that we were looking at the entire population. So we were acting like we've asked everybody. So let's just use the example of Bismarck High School. Before, we were looking at data where it was assumed that we asked every single kid at Bismarck High School. And that's good if you can do that, because that's the absolute best way to do it, because you actually ask every single person. The problem is, what if you want to collect data and you don't have the resources to actually ask every single student? It's a little bit tougher to ask every single student. Like, for instance, the attendance office. The attendance office has certain information about every single student here at BHS. Their date of birth, their home phone number, their home address. Not saying all of it's up to date, but they've gathered all of that. Now, let's say you wanted to run your own little experiment and you wanted to find out, what percentage of people live on the south of Main Street, or what percentage of students have phone numbers that start with 223 or anything like that. And if you were doing that, it might not be very easy for you to go out and ask every single student. And you could go to the attendance office, but they probably wouldn't share it because it's private information. And so the thing about this is that when it doesn't always work to ask the entire population, you have to take samples. Well, samples are good, but samples can vary depending on which kids you ask. And so that's what the central limit theorem kind of focuses on, is taking samples from the population. Okay? So, in addition to knowing about how individual data values vary about the mean for a population, so that's what the normal distribution tells us, is how values vary from the mean. Many times statisticians are interested in knowing how the means of samples of the same size taken from the same population vary about the population mean. So what we're talking about is, if one of you asks 10 students a question and another one of you asks a different 10 students a question, same question, and another person asks 10 more students same question, how much different are those answers going to be? Like, how much can we expect those answers to vary? And that's what the central limit theorem is based on. Okay? So what we have to know is what a sampling distribution is. It's a distribution obtained by using the means computed from random samples of a specific size taken from a population. So what that means is if we ask those 10 students a question, for instance, what's your GPA? Okay, we asked 10 students what their GPA is. If we took the mean of those 10 students, we'd get one number. And then somebody else asked 10 other students and found the mean, and you have one number. And somebody else asked 10 other students, and you found the mean, and now you have three numbers. Those three numbers become basically their own data points. Okay? So the means basically become data points. And that's kind of what the sampling distribution is. There's an error too, which is the difference between the sample measure and the population. Obviously, if you only ask 10 students their GPA, that's not going to represent the entire population of BHS. And so you have to keep that in mind, is that there is a little bit of an error because you're only asking for a sample. So the mean of the sample means should be the same as the population mean if you ask enough of them. Obviously, not one of them, not two of them is always going to match up. But if you take those means as separate data points and then you find the mean of all those, right? So those three numbers that we said we had in the last example, if you average those out, that mean should be very close to the population mean. Remember, the population would be all of BHS students. The standard deviation, however, is going to be smaller. And the reason is, by taking the mean, you're going to have less variation. If you ask 10 students your mean GPA, is going to get fairly, fairly exact, I should say. Very, it's going to be maybe in the high twos or something like that. And you might occasionally get some in the, in the low to mid threes or the low twos, but you're not going to have those outliers where if you ask individual students, you're going to get those outliers. That kid who has a 4.0 or the kid who has a 0.2 or something like that. You're going to get those drastic outliers where mean you don't necessarily have that. So here's your central limit theorem. As the sample size of n increases, so what we're talking about, the sample size was me saying we asked 10 students. As that size becomes bigger, the shape of the distribution of those means, taken with replacement, meaning we ask a student and we put them back in and they could possibly be drawn again, with a mean of mu and a standard deviation of sigma will approach a normal distribution. Okay? The mean of the sample means equals the population mean. Right there. So what this is this is the mean of the mean. And this is the population mean. The standard deviation, which we call the standard error, is calculated slightly different. You take the population standard deviation and divide it by how many, the n, how many, like the sample size, the square root of that number. Okay? So basically, the central limit theorem is used on the mean of samples. Okay, you have to keep that in mind, is that when you're taking a bunch of samples and you're calculating the means, each individual data value, each one of those means, should be treated as its own individual value. Okay, so the z-score basically stays the same. Just understand that this is the mean of the samples and this is the standard deviation of the samples. But because this is calculated the same, we can leave that the same. But remember, the standard deviation is calculated differently. Okay, so here's a quick example, and then we're going to do quite a bit more tomorrow on this. Nielsen reported, it's a sampling company, reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. Assume that the variable is normally distributed, and the standard deviation is about 3 hours. So if we ask 20 children between that age, and they're randomly selected, what's the probability that the mean of the number of hours they watch television will be greater than 26.3? This is very, very similar to what we were doing in the last section, except we're dealing with means, so we have a slightly different formula. So we're looking at that population. Okay? So since we are using like a bunch of samples, we have to use this formula for z-score. So that's basically the difference. So our number we're looking for is 26.3 minus 25 divided by standard deviation, except we have to divide it by the square root of 20. 20 is because we asked 20 students. Okay. That is 1.94. You go to the back of the book, you find 1.94 is 0.9738. And because we're going above, we take 1 minus that, which is 0.0262. So that means that's the probability of picking a sample and their mean being larger than 26.3. Okay? Now that was pretty quick. It's kind of an introduction. We're going to get into this a lot more, talk about it a lot more tomorrow.